Chapter 4, Descriptive Statistics. In this chapter, we're going to talk about the part of statistics called Descriptive Statistics. And it has two basic parts, which are known as central tendency and variation or dispersion. We should remember this from Chapter 1. Central tendency is finding the middle of the distribution of numbers, and the variation of dispersion is telling us how spread out they are. And what we're trying to do again is simplify the distribution. So if we look at the 28,000 students at UNLV and we look at their age, we'll find that the mean age of those students is 24 or 25, and that they have a lot of variation, that there's 16 and 17-year-olds and there's 70-year-olds, and they're spread out all over the place. If we did this at Penn State, we'd find the mean age of students is more like 20, and that the youngest is probably like 16 and the oldest is probably 23 or 24. I'm talking undergrads here, because they're out in the middle of nowhere in a little town, and their undergraduates are all regular age students who go there, and they're not an urban university like us that has students of all kinds of different ages and shapes and sizes. All right, so again, we're trying to find the middle. And there's three ways to do this, and you should remember that middle starts with an M, and the three ways we have to calculate central tendency all start with M's: the mean, the median, and the mode. There's actually a whole bunch more ways to calculate the central tendency, but there's only three we care about at this point: the mean, the median, and the mode. And again, we're trying to find the middle. So the mean, you've been calling it the average all your life. You know how to calculate it. Mean is mu is the population mean. We're going to calculate it. Mu equals sigma, which means sum of x, and x is an observation. So we're going to sum the observations. We're going to add up all the numbers. We're going to divide by capital N, which is how many numbers there are. It's the sample size or population size. So mu equals sigma x over n. We also have a unique way of writing the mean in statistics, which is the mean of a sample. If we have a sample, the mean of a sample has a letter with a bar over it. It's usually an X, so there's X bar. Anything with a bar, you see that little line drawn across the top of the X. Anytime you see that, that means a mean. Anything with a bar over it is a mean. So there are restaurants in Las Vegas that are means because they have bars over them. Anything with a bar over it is a mean. There's a third way we can say mean, which is called the expected value. And we write that E with the letter X in parentheses, and that's called expected value of X, E of X, which is, again, just a way of talking about the mean, but we only use that in certain circumstances. So, really simple. 2, 4, 6, 8. Want to find the mean of those four numbers? We add them up. We get 20. There's four of them, so we divide by 4, and we get 5. The median is that number, that observation to which half of the population of the sample is larger and half is smaller. So if we take the numbers 1, 2, 3, 4, 5, and we pick the number 3, there's two numbers smaller than 3, there's two numbers bigger than 3, and therefore 3 is the median. If we take our old friends 2, 4, 6, 8, 5 is the median, because 5 goes right in here, and there's two numbers bigger and two numbers smaller. If you've ever taken a test where they told you we were in a percentile, the median is the 50th percentile. It's that point where half are above and half are below. And then lastly, there's the mode. Mode comes from a French word that means fashionable, so pie a la mode is like fashionable pie. It's the observation that occurs the most often. That's how we know things are fashionable. We see them everywhere. So if I see the numbers 1, 2, 3, 4, and 4, 4 is the mode because there's more 4s than anything else. If I had 1, 2, 2, 3, 4, 4, then we would call that bimodal because there's two modes. If we have 2, 4, 6, 8, either there's no mode in there or it's quadrimodal. There's 4 modes. Okay, the mode isn't really a very useful thing because A, there might not be one, and B, it might not be anywhere near the middle, which is the whole point of central tendency. So when do we use the mean? We always use the mean. The mean has good mathematical properties. We like mathematics because we're statisticians, so we're always going to calculate the mean. When do we use or not use the median? We use the median when two things happen to us. One is when our distribution is skewed. Skewed means it's in one direction more than the other. So if we look at income, the median income in the United States for a household is about $50,000. It only goes down to zero, so it can't go very far down below 50,000, but there are people who make billions a year. Their income is much further out than the people who make little. So if we were to graph incomes look like this. Here's the middle, if you will, and there's not very many people. There's lots of people this way, but their numbers aren't very far away from the middle. And then there's the Bill Gateses and Steve Jobses who are way out here. This is skewed. If it's the same on both sides, like that kind of, that's not skewed. It's got the same over here that it has over here. Not skewed. We have words for that, and we'll talk about that later. The other possibility is outliers. An outlier is when all of us are here, but Albert Einstein is out here. You have a small number of people who are, or things, or whatever, who are far away from everybody else. Those things that are far away are called outliers. Outliers, skewed distributions, they mess with the numbers. The median income should be right here, kind of, but the mean income is going to be out here a little ways because these people are going to bias the average. They're going to pull the average way out. So when the government reports the income in the United States, they report median income, not mean income, because median income is more accurate as a way to tell us what's actually going on. And when we use the mode, we hardly ever use the mode. We don't care about the mode unless the mode is significantly more than anything else. So if in a typical week, if you survey what interest rate people paid when they bought a new house, 90% of all the people who buy a new house in Las Vegas in the same week will pay the same interest rate, and 10% will pay different interest rates. Because 90% pay the same rate, there's useful information in there, and then we would say the mode. But otherwise, we're not going to do that. Okay? All right. The second part of this is called dispersion, variation. Either one works. Variation to dispersion. Again, it measures how spread out the numbers are. So if it takes me 25 minutes to get to work every day, driving in, but some days it takes me 18, some days it takes me 40, that's the variation of my drive time. If you know someone's a 300 hitter in baseball, some days they're not going to get any hits, and some days they're going to hit everything. They're not always exactly at 3 out of 10. And you've got a basketball player who's normally hits 40% of their shots, but some days they miss them all. Some days they hit 20%. Some days they hit 70 or 80%. Okay, variation is natural. It's a normal phenomenon. Our problem is trying to separate out the natural from the unusual. But the variation of my drive time is normal. The most baseball hitters and basketball players, their ups and downs are a normal statistical thing. Okay? It's just natural that this variation occurs in our lives. All right. Simplest way to calculate this is something called the range. The range is actually not very useful. In the range, I take the largest number, subtract the smallest number. So in our case, I would take 8 minus 2 and get 6. This is not really useful because it doesn't tell me anything about any of the numbers in between. But sometimes it comes in handy. More fun is to begin to look at how far each point is away from the mean. So we calculate something called a deviation from the mean. And that's the distance of each point from the mean. So again, our numbers 2, 4, 6, and 8. The mean of those numbers is 5. 2 is 3 away from 5, but smaller. 8 is 3 away from 5 but larger. So we just calculate by subtracting the mean from each number. We take 2 minus 5 and get minus 3. That minus 3 is the deviation from the mean. It's how far that point is away from the mean. We get 4 minus 5 is minus 1. 6 minus 5 is 1. And the cool thing about the deviations from the mean is if we add them up, we always get 0. So on average, the deviation from the mean is 0. And here's a bad statistics joke. Statisticians are people who can stand in the kitchen with one hand in the stove and one hand in the fridge and say the temperature's fine because the deviations from the mean always add up to 0. This is really not useful. What we'd like to see is to be able to average these numbers. We can't average them because they always add up to 0. So you divide by 4 and you still get 0. So what are we going to do? We need to turn these minuses into a plus. But if we just did that and average them then, it's not going to work very well because it's not mathematical. There's math problems with doing that. So how do we get rid of the minus signs? The answer is we square everything. When we square them, 3 squared is 9. 1 squared is 1. 1, 9. When we square them, those negative signs go away. And now we can average these numbers. So if when we do that, we're creating something called the variance. And the variance is the average or mean squared deviation. The variance. So we just take our numbers that we just calculated, these deviations from the mean, we square them, we add those up, we get 20, we divide by 4, and now we get 5. Now there's a problem here. And the problem is a simple one. Let's suppose that, and I'm making this up, so don't go off and tell your friends, that this is the number of backpacks that were stolen in the library each month for the last 4 months. So there was a 2, a 4, a 6, and an 8, which would mean on average 5 backpacks per month were stolen in the library. And I have no idea. I'm assuming because all UNLV students are honest that actually no backpacks are stolen, but just for sake of the problem. Okay? So the mean is 5. 5 backpacks are stolen. And again, the fact that these are both 5 is just random. Don't worry about that. I calculate the variance of 5, but that's not 5 backpacks. This is 5 backpacks. 5 backpacks. This is 5 backpacks squared. Now, what's a squared backpack? I don't know. I know that 3 squared is 9, but I don't know what the backpack squared is. So the variance is an important number for us because we're going to do some stuff with it later. But it doesn't have a real world meaning because the units on it are squared. So what we're going to do, and again, here's the details of it for those of you that are detail people, and this is a mu, not an m, that's a mu. Sigma squared equals the sum of x minus mu squared over n. So sigma squared is the variance. That's the variance. Sigma squared is the sum of x minus mu, that's a deviation from the mean, right? That's a deviation. We squared those deviations, divide by n. Again, we don't like it because that makes us have squared units. The variance is sigma squared if it's the population, and we use s squared if it's a sample. But again, we need to do something. And what are we going to do? Well, if we have sigma squared, the easiest way to get rid of the squared would be to take the square root. So that's what we do. We create something called the standard deviation. And the standard deviation is the square root of the variance. So the square root of sigma squared is sigma. The square root of 5 is 2.23. And now in this case, that would be 2.23 backpacks. And now I know what it is. It's 2.23 backpacks. So you're saying, well, what can we do with that? Well, the answer is simple. Let's take our 5, which is the mean. That's mu. So on average, 5 backpacks are stolen. However, the standard deviation is 2.23. So if we go 2.23 below, we get 2.23 2.77. Right, that's a point. 2.77. Is 2.23 less than 5? 2.23 greater than 5 is 7.23. Okay? So that's 2.23 above 5 and 2.23 below 5. 2/3 of the time, from our numbers 2, 4, 6, and 8, which are the last 4 months, we conclude that 2/3 of the time, the number of stolen backpacks will be between 2.77 and 7.23. And 95% of the time, it'll be within 2. So basically between 0 and 10, 95% of the time you should have between 0 and 10 stolen backpacks. Okay? So the standard deviation is really, really useful to us. And we need to use the standard deviation and the mean. When we combine those two things, they tell us a world of stuff about our data. Just a ton of stuff about our data contained within those two numbers, the mean and the standard deviation. You will never see a real serious statistics problem. Well, not never, but almost never seen a real statistics problem that has no mean and no standard deviation to it. So how would we use this? Well, it turns out that finance professors use the standard deviation as a way to measure risk. So let's suppose a guy says to you, you give me $10 and I will invest it for you. And a year from now, I'll give you however much money I have, and that's either going to be 18, 19, 20, or 23. Okay? So the mean of those 4 numbers is 20. On average, that means I'm going to get $10 in profit for my $10 investment. That's pretty good for a year. The variance of those numbers is, and you see they don't vary much, right? 18, 19, 20, 23, that's not much of a difference between those numbers. So I would expect the variance to be small. I do the math. I take 18, 19, 20, 23. I subtract the mean of 20, 20, 20, 20, square them, add them up. Get 4, divide by 4, get 3.5. This is $20. The mean I'm going to get paid back is $20. This is squared dollars. 3.5 squared dollars. I have no idea what that means. But I take the square root and I get 1.87, which is $1.87. Now I know it's $1.87. I know what that means. Okay? So I have a variance here, which is fairly small. It's close to 0. There's hardly any variance. That means that this is not a risky investment. If I put my $10 in, I pretty much know what I'm going to get out. On the other hand, this guy says to you, I have another investment. And if you put $10 in, a year from now, I'll give you whatever I have. And it could be $5. It could be $6. It could be $20. But it could be $49. The mean of those 4 numbers is also 20. But those numbers are a lot more spread out than these numbers are. These numbers are all close together. These numbers are spread out. I do the math here. Take the 5, the 6, the 20, the 49, subtract the mean of 20, square them, add them up, divide by 4. Then take the square root. I get $17.75. The standard deviation is $17.75. Here it was 187. Here's 17.75. This investment is almost 10 times as risky as this investment. So this is a much riskier investment, but the most you could make here would be 23, and the most you could make here would be 49. So if you just wanted a nice, safe place to put your money, this would be it. If you want to take a chance on making a lot of money and you don't care about losing any money, this would be a lot more fun. Okay, so we can use that standard deviation to measure the riskiness of things. So again, descriptive statistics, mean, median, and mode. That's how we find the middle, the central tendency. We use the variance of standard deviation to find the variation or dispersion. There's 2 other numbers that are attached here. One is called the skewness. And again, the skewness tells us whether we have a skewed distribution or not. If we do the math on that, and I'm not going to show you how, but Excel, if you go do problem in Excel, it'll show you the skewness. That number should be close to 0. 0 means we're not skewed. A negative means we're skewed to the left, and a positive means we're skewed to the right, and tells us what our data look like. And then there's this thing called kurtosis, which tells us whether the distribution is peaked, or flat. And we hope actually it's neither one of those things. We hope our data are nice and kind of spread out and smooth, but kurtosis tells us whether things are peaked or flat. The bigger the kurtosis, the more peaked they are. The littler the kurtosis, the more flat they are. And again, Excel would tell us peakedness or flattedness of our data. Okay? And then there's one last thing we want to talk about. That's the coefficient of variation. Coefficient of variation is simple. It's the standard deviation divided by the mean. The point of that is it takes the units out. It gets rid of backpack. So we don't have to worry about it. We use the coefficient of variation to compare things that you wouldn't think normally could be compared. So if someone says to you, which varies more, the weight of an apple or the weight of an elephant? Well, your initial reaction is, hey, elephant. But it may be that all elephants weigh the same and all apples don't. So what we do is we take our numbers. Let's suppose that, and again, I made these numbers up. Suppose an apple on average weighs 10 ounces with a 5-ounce standard deviation, and an elephant on average weighs 80,000 ounces with a 20,000 standard deviation. Which varies more? Well, the answer is we do the math. We take the standard deviation divided by the mean, 5 over 10 for apples, 20,000 over 80,000 for elephants, and we get a half for apples and a quarter for elephants, and a half is bigger. So that says that apples vary more in weight than elephants.